Okay, so, in lecture 6 of Fox, we saw the sort of dizzying array of applications for induction and strong induction and leaping induction and all kinds of induction. It's important to recognize that all these types of inductions are basically the same, but some are more, common than others. Some problems are easier to tackle one way than another. Okay, and I mentioned in that lecture that there are these two interesting problems. Does there always exist a binary representation for an integer? Okay, which is a sum, which is a sum of distinct powers of 2. So any integer can be written as a sum of distinct powers of 2. Okay, so I'll go through the proof of that with strong induction. Just give you extra practice with strong induction, and then I'll go through the proof that that equal pile nim game, that game of strategy that we discussed, the equalization strategy guarantees player 2 a win. Okay, and again, we will use strong induction to prove that. So the first is binary representation, which is something we're all familiar with. Okay, binary representation of numbers. Okay, so let's take, for example, 18. We know what its binary representation is. To get its binary representation, we break it down, we decompose it into a sum of distinct powers of 2. So this guy here is 2 to the 4 plus 2 to the 1, which is 16 plus 2. Okay, and so now in the binary representation, we have the 2 to the 0th term, the 2 to the 1th place, the 2 to the 2 place, the 2 to the 3, the 2 to the 4. We have more, but we don't need to go beyond 2 to the 4 because the highest power of 2 is 2 to the 4. And so we represent this as, there's no 2 to the 0 term, there's 1. 2 to the 1 term, there's no 2 to the 2, there's no 2 to the 3, and there's a 2 to the 4. Okay. And so, 18 as a sum of distinct powers of 2 is 2 to the 4 plus 2 to the 1, and we compactly represent that in this binary representation of 18. Sometimes we'll say this number 10010 is 18 in base 2. Okay, and that's something that hopefully you're all familiar with, base 2. Okay, so something that you may not have thought about is it always possible? So let's prove that there exists a binary representation for every natural number n. And in fact, it's also the case that the binary representation is unique. So two different numbers cannot have the same binary representation, and a given number cannot have more than one binary representation. Okay. But let's at least prove that it exists. There always exists a binary representation. So, for all n greater than or equal to 1, there is a binary representation, i.e. n is a sum of distinct powers of 2. Okay, now let's define a predicate that goes along with this. So P of n is the claim that n is a sum of distinct powers of 2. Okay, so that's a predicate. Okay, and now, how would I go about convincing you that a particular integer can be written as a distinct power, as a sum of distinct powers of 2? Okay, so we may have sort of difficulty in sort of seeing this in the abstract setting. Okay, but now we are in this induction lecture, so you must think, okay, so if I'm trying to convince you about some number being a sum of distinct powers of 2, maybe I can use the fact that some smaller numbers are distinct is a sum of distinct powers of 2. So let's take an example. Let's say 24. So I want to convince you that 24 is a sum of distinct powers of 2. Okay. Well, this is an example of an even number. Okay. So look, okay, let me divide by 2. I get 12. Okay, and I know that 12, it's easy for me to represent 12 as a sum of distinct powers of 2. Okay, so this is equal to 2 cubed plus 2 squared, because 12 is smaller, so it's an easier problem for me to deal with. But now since 24 is twice that, so 24 is equal to 12 times 2. So if I multiply each term by 2, I get 2 to the 4th plus 2 cubed. And there, 24 is represented as a sum of distinct powers of 2. And all I needed to do that was to know how to do it for 12. So if I could do it, if I could represent this smaller number 12 by a sum of distinct powers of 2, I can do it for 24. Okay? And now we're starting to think, so induction might be relevant, because if I can solve it for the smaller problem, okay, if I can make the claim for the smaller problem, it implies the claim for the larger problem. Except this is a much smaller problem. It's not n minus 1. It's not the previous one, which would be ordinary induction. So this is an indication that maybe strong induction is what we need. Let's do the next case, which is 25. So how would I convince you that 25 is a sum of distinct powers of 2? Well, in this case, 25 is odd, so I can consider the smaller number 24. Okay. Now, since 24 is smaller, typically in induction, we sort of assume that the smaller guy can be solved. Okay. That's the basic idea. So if I can represent 24 as a sum, and I know I can, so here, 24 is equal to 2 to the 4 plus 2 to the 3. One thing I know for sure is that there's not going to be any 2 to the 0 here. Why? Because 24 is even. Okay? So it can only have powers of 2 that are strictly greater than 0. There's no 2 to the 0 which is equal to 1. Because if there were a 2 to the 0 term, then you'd have 1 plus all even numbers, okay, and then that 1 would make it odd. And we know that 24 is even. So there's no 2 to the 0 term. Okay, so I can get, if I add the 2 to the 0 term, I'm simply adding 1, and I know this wasn't there before, so it's a new power of 2 that I'm adding, and I know that this must equal 24 plus 1, which is 25. So there, if I have an even number, like 24, I can divide by 2, use the sum of distinct powers of 2 for that smaller number, and then multiply and add 1 to each power. If I have an odd number, I can consider the expansion for, the number that's 1 less and add 2 to the 0. Okay? And that's the basic idea behind the proof by induction. So let's now prove it. So we prove, so claim P of n is true for all n. P of n is true for all n greater or equal to 1. Okay? So what does that say? That every natural number can be represented as a distinct sum of powers of 2. As a sum of distinct powers of 2. Okay, so proof. And now we're going to use strong induction. And if you're ever in doubt what induction to use, go for strong induction. Because remember, we already showed that it's never harder to prove something with strong induction. Induction is always easier, and it basically accomplishes the same thing as induction. Okay, so base case. We know that 1, so P of 1, is clearly true because 1 is equal to 2 to the 0, which is a sum of distinct powers of 2. So true. Induction step. Good. That was the induction step. The induction step claims that what we have to do, we have to show that P of 1 and P of 2 and P of 3 and P of n, okay, implies P of n plus 1. So this is the strong induction implication. And this is a much easier implication to prove because unlike the regular induction implication where we only get to assume P of n, here we get to assume P of 1 and 2 and 3 all the way up to n. So assume P of 1 and P of 2 and P of n. Okay, so assume that all numbers less than n plus 1, so from 1 to n, have a distinct representation, have a sum of, have a representation as a sum of distinct powers of 2. Okay, good. Okay. So now let's consider n plus 1. N plus 1. There are two cases. It's either even or n plus 1 is odd. Okay. If n plus 1 is even, then n plus 1 over 2 is strictly less than n plus 1. Okay, because n plus 1 is at least 2. Okay, so n plus 1 over 2 is strictly less than n plus 1, which means that it's one of these numbers which means that the claim holds for n plus 1 over 2. So, which means that the claim holds for n plus 1 over 2. So n plus 1 over 2 is equal to a sum of distinct powers of 2. So we can say it's equal to 2 to the power d1 plus 2 to the power d2 plus and so on, 2 to the power dk. Okay, well, we don't know what k is. It could be, it could be a sum of many distinct powers, or it could be a sum of just one, but we don't care. All we know is that these are distinct. So therefore n plus 1, so this implies that n plus 1 is equal to 2 to the d1 plus 1 plus 2 to the d2 plus 1 plus and so on plus 2 to the dk plus 1. And since the d's here are all distinct, it means that when you add 1 to all of them, they remain all distinct. Okay? And so this means that n plus 1 is a sum of distinct powers of 2, as was to be shown. So this is the case that n plus 1 is even. If n plus 1 is odd, then n is even. So therefore, 2 to the 0 is not in the sum for n. So 2 to the 0 is not in the sum for n, which means that we can add it into the sum and move up 1, which means that n plus 1 is equal to the sum for n plus 2 to the 0. Since this is distinct powers of 2 that do not include 0, and now I've added a term 2 to the 0, okay, so this is whatever, this is n, and this is 1. And none of these powers are 2 to the 0, so all the powers on the right-hand side are distinct. And so therefore, n plus 1 in this case is also a sum of distinct powers of 2. So what's the conclusion? The conclusion is that we have proved that Pn plus 1 is true. Therefore, Pn plus 1 is true. And that concludes the proof of what? Of this implication. It's a little bit more sophisticated than what we saw before, but that's what we set out to do, prove this implication. The proof of this implication involved a couple of cases. That's perfectly fine, no problem. And what's the final conclusion? The final conclusion is by induction, P of n is true for all n greater or equal to 1. End of proof. End of proof by induction. Every number n has a binary expansion, has a representation as a sum of distinct powers of 2. In fact, we can now sit down and try to think, how would I prove that that representation is unique? There are no two different ways to represent a number as a sum of distinct powers of 2. Okay, let's erase, and I'll show you one final application of strong induction. Okay, and it is to games of strategy. So induction and strong induction are used to prove things about greedy algorithms, about recursions, about dynamic programs. These are all algorithmic design techniques that you will learn, or maybe you already learned. Okay, you will learn them when you take an algorithms class. Okay, and when you design games of strategy, inductions are very often the tool that allows you to find and prove optimal strategies. Okay. So let me introduce you to a game of strategy called NIM. Okay, so NIM. And let's call this 2 pile pile NIM. 2 equal pile NIM. Okay. And in the live class usually I find a volunteer from among the many students who are going to challenge me to a game of equal pile NIM. Okay. So what's NIM? NIM is this is this word that means to steal or to pilfer. Okay. So imagine that you have two piles of coins, and I'm showing you two piles with 5 coins. So pile 1, pile 2. Okay. And this is a very simple application of strong induction, but just to show you that we can use induction to analyze games of strategy. Okay, so now the idea in NIM is that you have two players, so you have player 1 and player 2, and they take turns. So take turns, picking any number of coins you want from one of the piles. Okay, picking coins from one pile. And the last person to be able to pick coins is the winner. Okay? So I ask you, you want to go first or second? And usually it looks like an advantage to go first. So, let's say as player 1, you go first and you pick all the coins from this pile. Well, then you've lost immediately. Okay? Because player 2 comes along and bam, picks all of those coins. So you can't pick all the coins from one of the piles. So the interesting situation arises if you start by picking, let's say, 2 coins. So there were 5, and player 1 starts by picking 2 coins. Now what? Okay, so now what does player 2 do? Okay, so I'm going to show you a very interesting strategy. It's called the equalization strategy. And in fact, this strategy shows that player 2 always can arrange to win. So it's better to be player 2 in this game of of 2 equal pile NIM. Okay, and here's player 2's very simple strategy. Whatever player 1 did, I will do the same thing to the other pile. So in this case, player 1, remove 2 coins. So I will remove 2 coins from here. Okay, interesting. So, okay, does that work? And that's the question. And so we're going to analyze this strategy. And I'm going to prove to you that player 2 always wins with this strategy. So the equalization strategy. So claim the equalization strategy guarantees a win for player 2. What was the equalization strategy? Whatever player 1's move, so even now, okay, so player 1 needs to move. So maybe player 1 changes their mind and says, I'm going to take from pile 2. So I take 2 from pile 2. So player 2, what does player 2 do? Does exactly the same thing to the other pile. So it takes 2 from the other pile. And why do we call it an equalization strategy? Because look what it accomplishes. It renders the 2 piles equal. Okay. And I claim that no matter how many coins were in the 2 piles to start with, player 2 wins with this equalization strategy. And now let's see the proof. Okay, so proof. So let's define a claim, P of n. Player 2 wins when both piles have n coins. Okay. And we want to make the claim that, no matter what n, player 2 wins. So for all n greater or equal to 1, let's say, P of n. So player 2 wins no matter how many coins are in the 2 piles to start with. Okay, so let's see the strong induction proof at work. Okay, proof. Okay, so strong induction. Okay, so the base case. Okay, so P of 1 means there's 1 coin in each pile. So there's just 1 coin in each pile. Okay, and player 1 has to take 1 coin from one of the piles, and player 2 takes the other coin and is the last person to play, and therefore wins. So player 2 wins, and so we have a check mark here. Nice. Okay, now the induction step. This is the tricky step. The induction step. Okay, and well, if I forgot to mention it, it should have been kind of obvious that a player on their turn has to take at least 1 coin. Otherwise, the game never ends. Everyone takes 0 coins. Okay, so the induction step, we have to prove that, and if we're doing strong induction, we have to prove that P of 1 and P of 2 and so on, and P of n implies P of n plus 1. So we get to assume P of 1 and up to P of n. And you might be asking, man, this induction game, you're always assuming things. Remember, we're not assuming anything. Okay? We're just using an assumption in the proof of an implication. So this is a technique for proving an implication. We're not assuming this is true. We're just saying that in order to prove this implication, we're going to jump into this world where that's true and see what happens. Okay? We need to prove P of n plus 1. So you have n plus 1 coins in both piles. Okay, so you have n plus 1 coins. Well, we'll also consider two cases. The first case is that player 1 takes all the coins from one pile. Okay, so player 1 takes all coins from one pile, and that's no problem. Okay, the equalization strategy says player 2 take all coins from the other pile and you've immediately won. Okay, so no problem. Player 2 wins. I'll use P2 to say player 2 wins. Okay, then the other case is that player 1 doesn't empty a single pile, so player 1 leaves k less than n plus 1 in a pile. Okay, so he takes some number of coins, leaving k, but we don't know k, because player 1 could take 1 coin, in which case he's left n. Could take 7 coins, in which case he's left, n plus 1 minus 7. Okay, so we don't know k, and that's the critical use of the induction, the strong induction hypothesis. Okay, so what we know is that the situation is like this. We have k in one pile, and we have n plus 1 in the other pile. Okay, and now the equalization strategy says, you know what? Reduce the other pile to k by taking the same number. So player 2 takes this stuff away. So this is player 2, takes this away and reduces it to k and k. Okay. So that's just a smaller instance of the same game. And now it's player 1's turn to play. And the strong induction hypothesis says that no matter what k is, as long as it's between 1 and n, which we know, okay, as long as it's between 1 and n, we know that player 2 wins. So player 1's turn to move, so player 2 wins in this game. So player 2 wins this game by the strong induction assumption. What's that? That's this assumption. Okay, we assume that P of 1, P of 2, up to P of n are true. So therefore P of k is true, which means that player 2 wins the game with k coins in each pile, as long as k is less than n plus 1. Okay. And so that means that player 2 wins the game with n plus 1. So therefore, P of n plus 1 is true, which is all we had to prove. And that ends the proof. By induction, P of n is true for all n greater equal to 1. There! So we've just proved that the equalization strategy wins equal pile nim, okay, no matter how many coins started. What about if it was unequal pile nim? Who wins? Think about it for a couple of seconds. If you said player 1 wins, if it's unequal pile nim, then you're right, prove it by induction. And, it's an interesting question. What about if you have more than one pile? More than 2 piles? That's a very interesting question. But we won't get to that question here. Just to show you the range of things that induction and strong induction can be used for. And just in this lecture, we saw, proving inequalities. We saw proving statements about tilings of grids using, let's say, L tiles. We saw, the fundamental theorem of arithmetic. We saw the binary representation of integers. And we saw analysis of games of strategy. Very simple strategy guarantees a win for player 2. Okay. So, it's very important to learn induction. Okay, for computer science especially, and just in general, just this concept that if I can answer a question or solve a problem for a small value of n, then I can solve it for a bigger value of n. So that concept that if I can build a link from a small n to a big N, then I can solve the problem for all n. Just that concept is very important, and we'll discuss it more when we talk about recursion next. Okay. So chapters 4, 5, and 6. If you're going to read any chapters very, very carefully, those are the ones to read carefully right now. And ciao.